In October 2024, NASA launched a spacecraft on a mission that most scientists working in astrobiology consider the most important planetary science mission since the Voyager probes. Its target is not a distant star. It is not a black hole or a nebula or a galaxy. It is a moon of Jupiter, 628 million kilometers from Earth at closest approach, covered in a shell of ice circling the solar system's largest planet once every 3.5 days. A moon that, if the current scientific understanding is correct, contains more liquid water than all of Earth's oceans combined, beneath several kilometers of ice, kept liquid not by proximity to the sun, but by the tidal forces exerted by Jupiter's gravity, squeezing and stretching the moon's interior like a rubber ball. That moon is Europa, and the spacecraft, the Europa Clipper, is going to try to find out whether anything lives in that ocean. That is not hype. That is the actual scientific mission statement. The official NASA mission objective for Europa Clipper is to investigate whether Europa has the conditions necessary for life: liquid water, chemical energy sources, and the right chemistry. If it finds what the models predict it should find, the next question will be whether to build a lander. But Europa is not the only surprise in Jupiter's neighborhood. In the last few years, a series of discoveries from the Juno spacecraft, which has been orbiting Jupiter since 2016 and has been conducting flybys of Jupiter's moons in its extended mission, have rewritten what we thought we knew about the Jovian system. Io, the innermost large moon, has been revealed in close-up as the most volcanically active body in the solar system by a wider margin than anything we previously imagined. Ganymede, the largest moon in the solar system, has a subsurface ocean of its own and a magnetic field, which has profound implications for that ocean's habitability. Even Callisto, the outermost of the 4 Galilean moons, is showing signs of internal structure more complex than the simple, frozen, undifferentiated ball we assumed it was. Jupiter's moons are not just interesting objects. They are, in aggregate, a miniature solar system, 4 large worlds with radically different compositions, histories, and internal dynamics, orbiting a central body that has more mass than all the other planets combined. Understanding them is, in a very direct sense, understanding whether life can arise in the cold outer solar system, and by extension, in the icy moon systems of Saturn, Uranus, and Neptune, and ultimately around the countless ice giant exoplanets that appear to be the most common type of planet in the galaxy. This video is going to start with what we knew before and what we've just discovered, and then go where the science actually leads, which is toward one of the most profound open questions in human history. Chapter 1: The Galilean Moons, a brief history of 4 worlds. On the evening of January 7th, 1610, Galileo Galilei pointed his newly improved telescope at Jupiter and noticed 3 small bright points of light arranged in a line near the planet. The following night, they had moved. The night after, one had disappeared and reappeared on the other side. Within a week, he had tracked 4 distinct objects that were clearly orbiting Jupiter, not orbiting Earth, not fixed to the celestial sphere, but circling another planet in patterns that obeyed the same gravitational logic as everything else he was observing. The observation was politically explosive. The heliocentric model of Copernicus required that not everything in the sky orbited Earth. Here was direct, visible proof: 4 moons circling Jupiter as clearly as the moon circles Earth. It didn't prove heliocentrism by itself, but it demolished the most intuitive objection to it. Galileo published the discovery in Sidereus Nuncius, The Starry Messenger, in March 1610, 2 months after he first observed what would become known as the Galilean moons, Io, Europa, Ganymede, and Callisto. For 3.5 centuries, these moons were points of light, bright, measurable, orbitally precise points of light whose existence had changed human cosmology, but points of light nonetheless. Their surfaces, compositions, and internal structures were entirely unknown. That changed with the Pioneer 10 and 11 flybys in 1973 and 1974, which provided the first close-up photographs. But it was the Voyager 1 and Voyager 2 flybys in 1979 that transformed the Galilean moons from points of light into worlds. The Voyager images revealed Io's volcanic eruptions in progress, the first active volcanoes ever observed outside Earth. They revealed Europa's ice-covered surface, crossed by a network of lines and cracks, suggesting a subsurface ocean below. They revealed Ganymede's complex geology, ancient craters and grooved terrain, suggesting a violent geological history. And they revealed Callisto's densely cratered, ancient surface, apparently unchanged since the early solar system. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, was one of the most scientifically productive planetary missions ever flown. Over 8 years of Jupiter operations, it conducted 11 close flybys of Europa, 8 of Ganymede, 8 of Callisto, and 7 of Io, plus multiple passes through Jupiter's ring system and deep atmospheric monitoring of the gas giant itself. Each flyby returned data in multiple wavelength ranges and from multiple instruments simultaneously. Imaging, near-infrared spectroscopy, magnetometry, plasma wave measurements, and particle measurements. The cumulative dataset from Galileo's Europa flybys told a consistent story across multiple independent measurement types. The magnetometer found the induced magnetic field signature expected from a saltwater ocean. The plasma wave instrument found evidence for a torus of material in Europa's orbital path, consistent with material being ejected from the surface. The near-infrared spectrometer found hydrated salts on the surface. The imaging system found the complex ridged and disrupted terrain that is best explained by a dynamic, active ice shell in communication with a liquid layer below. Each individual measurement was explicable by alternative hypotheses, but the combination of all of them pointing in the same direction was essentially conclusive. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, built enormously on the Voyager reconnaissance. Its magnetometer detected distortions in Jupiter's magnetic field near Europa and Ganymede that were exactly what you would expect if these moons contained electrically conducting fluids, specifically saltwater oceans, being pushed through the magnetic field as the moons orbited. This was the first strong evidence that the subsurface oceans of the Galilean moons were real rather than hypothetical. The Galileo mission ended when the spacecraft was deliberately steered into Jupiter's atmosphere on September 21, 2003, to prevent the risk of an uncontrolled collision with Europa that could potentially contaminate any subsurface biosphere with Earth microbes carried on the spacecraft. The fact that NASA intentionally destroyed a functioning, expensive spacecraft to protect the possibility of life in Europa's ocean is itself a statement about how seriously the scientific community takes the habitability question. The next chapter began with Juno. Launched in 2011, Juno arrived at Jupiter in July 2016 and spent its primary mission studying Jupiter's atmosphere, gravity, and magnetic field from a highly elliptical polar orbit that brought it inside the planet's radiation belts. In 2021, as Juno's primary mission ended, NASA extended the mission to include flybys of the Galilean moons. Juno has since conducted close flybys of Ganymede in June 2021, Europa in September 2022, and Io in December 2023 and February 2024, collecting data at resolutions and in wavelength ranges previously unavailable for these moons. The Io flybys in particular, coming within 1,500 kilometers of the surface, returned images and measurements that have genuinely shocked planetary scientists. Chapter 2: Io, the most volcanic world we've ever seen. Io was the first surprise. When Voyager 1 returned images of Io in March 1979, the photographs showed a surface that looked, as one scientist described it, like a pizza, splotched with red, orange, yellow, and white, with no impact craters anywhere. The absence of craters was the key. In the solar system, any surface exposed to space long enough accumulates craters from meteorite impacts. The older the surface, the more craters. Io had none, meaning its surface was being continuously resurfaced and wiped clean. One Voyager scientist, Linda Morabito, noticed what appeared to be an umbrella-shaped cloud above the limb of Io in one image, a volcanic plume actively erupting. Io was volcanically active, in real time, in the image taken during the flyby. The discovery was theoretically anticipated, just barely. 3 days before the Voyager, one flyby, Stanton Peele, Patrick Casson, and Ray Reynolds had published a paper in Science predicting that tidal heating from Jupiter's gravity would make Io's interior molten. The paper was published on March 2, 1979. The Voyager flyby revealing the volcanic activity was on March 5, 1979. The prediction and the confirmation arrived in the same week. Tidal heating works as follows. Io's orbit around Jupiter is not perfectly circular. It is slightly elliptical, maintained in that eccentricity by gravitational resonances with the other Galilean moons, particularly Europa and Ganymede. In a specific configuration called the Laplace resonance, Io orbits Jupiter exactly 4 times for every 2 orbits of Europa and exactly 1 orbit of Ganymede. This resonance prevents Io's orbit from circularizing. Every time it approaches a circular orbit, the gravitational tug from Europa perturbs it back into an elliptical one. The elliptical orbit means Io's distance from Jupiter varies through each orbit. Since Jupiter's tidal gravity scales with the inverse cube of the distance, the tidal force stretching Io toward Jupiter is larger when Io is close and smaller when it is far. As Io moves through its orbit, its shape changes. It is stretched toward Jupiter at closest approach and returns to a more spherical shape at farthest approach. This periodic stretching and relaxing of the rock generates internal friction, which generates heat. The heat generated by this process is called tidal dissipation, and for Io, it is the primary energy source driving its volcanic activity. The total tidal heating power of Io has been measured from orbital mechanics and from direct infrared observations of the heat escaping from its surface. The result? Approximately 100 terawatts of power, about twice Earth's total internal heat flow from radioactive decay averaged over the entire surface area. This is an extraordinary number for a moon that has roughly the same size and mass as Earth's moon, which is geologically dead and cold. Io's interior is kept hot not by radioactive decay, but by the mechanical energy of its orbit around Jupiter, transferred to heat by the tidal flexing of its rock. What does 100 terawatts of internal heat look like on the surface? It looks like approximately 400 volcanoes in various states of activity, many producing eruption plumes that extend hundreds of kilometers into space. It looks like lava lakes the size of small seas. Loki Patera, Io's largest lava lake, is an irregular dark lake of molten rock approximately 200 kilometers across, larger than the state of Ohio, periodically overturning as the cooled crust on its surface sinks and is replaced by fresh lava from below. It looks like eruption plumes that deposit sulfur dioxide frost in rings hundreds of kilometers wide around their vents, giving Io's surface its distinctive splotchy coloration. And it looks like mountains, some of the tallest mountains in the solar system, reaching over 18 kilometers, formed not by plate tectonics, but by the compressional stresses as Io's crust is continuously buried under new lava flows and pushed upward. The Juno flybys of December 2023 and February 2024 produced the most detailed close-up observations of Io's surface in 20 years, since the Galileo spacecraft last flew close to it. The images and measurements from these flybys have revealed volcanic activity at a scale and character that surprised even scientists who had spent decades studying Io. The closest approach was in February 2024, at just 1,500 kilometers above the surface, closer than any spacecraft had come to Io since the Galileo mission. The images returned showed multiple simultaneous eruptions in progress, including at least two that were producing extraordinarily large lava flows, rivers of molten rock extending hundreds of kilometers from their source vents. One of these flows, associated with a feature called Pele, named after the Hawaiian goddess of volcanoes, showed lava temperatures as high as 1,600 degrees Celsius, hotter than most lava on Earth, and consistent with a rock composition similar to komatiite, a type of magnesium-rich lava common in the ancient Earth, but rare today. The high temperatures suggest that the lava erupting from Io's most active vents is not ordinary basalt, but is more primitive, hotter rock from deep in the mantle, material that on Earth was last erupted routinely in the Archean, more than 2.5 billion years ago. But the most striking finding from the Juno-Io flybys was not the lava temperatures or the eruption plume heights. It was what the observations revealed about the global pattern of volcanic activity and what it implies about Io's interior structure. Simple tidal heating models predict that the heat generated inside Io should be concentrated where the tidal stresses are largest, which is near the poles and at specific longitudes relative to Jupiter. If the heat is generated predominantly in the interior and transported outward through the mantle, the volcanic activity should be most intense in these predicted locations. What Juno found, comparing the locations of active volcanic centers to the predictions of tidal heating models, is that the observed volcanic distribution does not match the simple model predictions particularly well. The heat is not concentrated where the models predict. Either the tidal heating distribution inside Io is more complex than the simple models assumed, or the heat transport mechanism, how heat moves from where it is generated deep in the mantle to where it erupts at the surface, is operating in ways the models don't capture. The specific numbers from the Juno flybys make this heat distribution puzzle vivid. The predicted volcanic hotspot distribution from standard tidal heating models places the maximum volcanic activity at latitudes around 30 to 50 degrees, both north and south, and at a specific sub-Jovian and anti-Jovian longitude. The observed distribution from Juno's JIRAM, Jovian Infrared Auroral Mapper, instrument, which can detect the thermal emission of hot lava even through Io's tenuous atmosphere at resolutions better than 10 kilometers per pixel, shows that many of the most thermally active volcanic centers are located at lower latitudes and at different longitudes than predicted. Some of the highest temperature features Juno detected are near the equator, where simple tidal heating models predict relatively modest heat generation. One proposed resolution is that Io's mantle is not a simple rock structure, but contains a partially molten layer, an asthenosphere, analogous to Earth's asthenosphere, but more extensive, that preferentially conducts heat in ways the simple models don't capture. 2. Io's upper mantle contains a significant fraction of melt. Perhaps 20 to 30% of the rock is molten at any given depth, rather than the much smaller melt fraction in Earth's mantle. The rheology, flow behavior, of this partially molten layer could redistribute the tidal heating signal in ways that smear it away from the predicted locations. The Juno data is motivating new interior models that treat Io as a body with extensive partial melt in the upper mantle, rather than the solid rock plus discrete magma chambers picture that earlier models assumed. This matters for Europa. If the principles controlling heat transport in tidally heated rocky interiors are not well understood, as the Io heat distribution discrepancy suggests, then models of tidal heating in Europa's rocky interior, which depend on similar physics, carry corresponding uncertainties. The hydrothermal activity that Europa models predict at the seafloor depends on how much heat is reaching the base of the ocean from the interior below, which depends on how heat is generated and transported in the rock layer beneath the ocean. If Io is teaching us that these models are wrong in a systematic way, the predictions for Europa's seafloor heat flow, and therefore for the intensity of hydrothermal venting that might support a chemosynthetic biosphere, need to be revisited. This discrepancy is not a minor technical detail. It is telling us that our fundamental understanding of how tidal heating works inside a rocky body is incomplete. This matters not just for Io, but for every other tidally heated body in the solar system and beyond, including Europa and Enceladus, and potentially many of the exomoons that may exist in outer solar systems around giant planets. Chapter 3: Europa, the Ocean. World. Europa is, of all the objects in the solar system beyond Earth, the most compelling candidate for extraterrestrial life. This is not a fringe opinion. It is the mainstream position of the astrobiology community, supported by decades of evidence and endorsed by the formal priority-setting process of the planetary science community, which ranked Europa exploration at or near the top of its recommendations in the 2023 to 2032 Planetary Science and Astrobiology Decadal Survey. The case for Europa's habitability rests on three pillars that are well established by current evidence, and one ingredient whose presence is strongly inferred but not yet confirmed. The three established pillars are liquid water, a chemical energy source, and stability over long timescales. The unconfirmed but strongly suspected ingredient is the chemistry, specifically the presence of the organic and inorganic compounds needed for the biochemistry of life. Liquid water is, by all current understanding, the single most important prerequisite for life. Not just any liquid water, specifically, liquid water in contact with rock over long timescales, which enables the geochemical reactions that produce the chemical gradients and reactive compounds that drive metabolism. Europa's ocean is estimated to be 60 to 150 kilometers deep, sitting beneath an ice shell estimated to be 15 to 25 kilometers thick. The ocean is in direct contact with Europa's rocky seafloor at the bottom. The water has been in contact with this rocky seafloor for geological time, potentially billions of years. The volume of that ocean is approximately twice the volume of all of Earth's oceans combined. Europa is 90% the size of Earth's moon in radius. It is not a large body, but the volume of liquid water it contains is potentially enormous because it is so deep. If there are organisms in Europa's ocean, there is room for an enormous biosphere. The chemical energy source for the ocean is provided by two mechanisms, both of which are well grounded in physical chemistry and observational evidence. The first is hydrothermal venting at the seafloor. Europa's rocky interior is heated by a combination of radiogenic decay, the same radioactive isotopes that heat Earth's interior, and tidal heating from Jupiter's gravity. The heat drives water circulation through the rocky seafloor, producing hydrothermal fluids. On Earth, hydrothermal vents on the ocean floor support rich ecosystems entirely independent of sunlight, based on chemosynthesis. Organisms using the chemical energy in the reduced compounds, hydrogen sulfide, hydrogen, methane, released by the hot vents to build organic molecules. This chemosynthetic pathway is the most likely route to life in Europa's ocean if life is there. The hydrothermal venting scenario for Europa is not merely theoretical. It is grounded in what we observe in analogous systems on Earth. Earth's mid-ocean ridge system, where tectonic plates spread apart and hot mantle rock wells up to fill the gap, hosts a global network of hydrothermal vent fields. The most biologically productive of these are the black smokers, hydrothermal vents that expel superheated, mineral-laden water at temperatures exceeding 350 degrees Celsius directly into the cold, deep ocean, precipitating metal sulfides as the hot fluid mixes with the cold seawater. The ecosystems around black smokers include tube worms up to 2 meters long, vast colonies of chemosynthetic bacteria, crabs, shrimp, and fish, all in conditions of total darkness, at pressures of several hundred atmospheres, supported entirely by chemosynthesis rather than photosynthesis. The even more compelling analog for Europa may be the alkaline hydrothermal vent systems. Systems like the Lost City hydrothermal field, discovered in the mid-Atlantic in 2000. Lost City vents operate at lower temperatures, 40 to 90 degrees Celsius, than black smokers, and they are driven not by proximity to a spreading center, but by a process called serpentinization. When seawater infiltrates fractured mantle rock composed of olivine and pyroxene, a chemical reaction converts these minerals to serpentine, releasing large amounts of hydrogen and methane in the process. The hydrogen produced by serpentinization is a potent energy source for microbial life. Microorganisms can use it as a fuel in combination with dissolved carbon dioxide to produce organic matter. Lost City is particularly relevant to Europa because serpentinization does not require a spreading center. It only requires liquid water in contact with the right kind of rock. And it could occur across Europa's entire seafloor, wherever the rock composition is appropriate. The second energy source is more unusual and is specific to Europa's location near Jupiter: radiolytic oxidant production. Jupiter's powerful magnetic field traps energetic charged particles, protons and electrons, in radiation belts surrounding the planet. These particles continuously bombard Europa's icy surface, bombarding the ice with enough energy to break water molecules apart through radiolysis. The products of this radiolytic chemistry include hydrogen peroxide, sulfuric acid, and various oxidizing compounds. These oxidants accumulate in the surface ice, and if they are mixed down through the ice shell to the ocean, can react with the reducing compounds produced at the hydrothermal vents to release chemical energy. The combination of hydrothermal reducing agents at the seafloor and radiolytic oxidants from the surface, mixed in the ocean, creates a chemical disequilibrium, a battery, essentially, that provides a persistent energy source for any chemistry or biology operating in the ocean. Whether the radiolytic oxidants actually reach the ocean depends critically on how the ice shell works. If the ice shell is entirely rigid and conductive, a simple layer of cold solid ice with no internal dynamics, then the surface chemistry stays at the surface and never reaches the ocean. But there is substantial evidence, particularly from the surface morphology of Europa as imaged by Voyager and Galileo, that the ice shell is not entirely rigid and that surface material is being cycled into the interior through a variety of mechanisms. The surface of Europa is one of the smoothest in the solar system in terms of topography. The highest features are only a few hundred meters tall, but it is crossed by a complex network of ridges, bands, and disrupted terrain that has no analog on any other solar system body. The ridges, double ridges with a central trough, some stretching for thousands of kilometers across the surface, are thought to form when subsurface water or warm ice is squeezed upward through cracks in the shell, freezing and building up on either side. The bands, regions where the ice has pulled apart and been filled with new material, suggest that sections of the ice shell have moved relative to each other, like tectonic plates on Earth. And the most striking terrain type, called chaos terrain, shows regions where the ice appears to have partially melted from below, broken into rafts that rotated and tilted, and then refroze in the disrupted positions. Chaos terrain suggests episodes of direct communication between the ocean below and the ice shell. If the ice shell is indeed active in this way, cycling surface material to depth and bringing ocean material to the surface. Then the radiolytic oxidants produced at the surface can potentially be delivered to the ocean, and the products of ocean chemistry can potentially reach the surface, where they could be detected by a spacecraft flying by. Chapter 4: The Europa Clipper. What it's actually going to do. On October 14th, 2024, the Europa Clipper launched aboard a SpaceX Falcon Heavy rocket from Kennedy Space Center. It is now on a trajectory that will take it to Jupiter via a gravity assist from Mars in February 2025 and another gravity assist from Earth in December 2026, arriving at Jupiter in April 2030. Once at Jupiter, it will enter orbit not around Europa itself. The intense radiation environment of Jupiter's inner magnetosphere makes a Europa orbit too damaging for the spacecraft's electronics, but around Jupiter, making 49 close flybys of Europa over the course of approximately 4 years. The reason for flyby science rather than orbiting Europa is worth explaining, because it illustrates a fundamental constraint on every scientific mission to the Jovian system. Jupiter's magnetic field is the largest and most powerful in the solar system, extending millions of kilometers from the planet. Charged particles trapped in this magnetic field, electrons and protons spiraling along magnetic field lines, are concentrated in radiation belts in the inner Jovian system, exactly where Europa orbits at 670,000 kilometers from Jupiter's center. The radiation environment at Europa's surface is about 1,000 times more intense than Earth's Van Allen belts. For electronics, this is deeply damaging. Silicon semiconductor devices accumulate radiation damage that degrades their performance and eventually causes failure. The Galileo spacecraft, which orbited Jupiter and made multiple Europa flybys, suffered significant radiation damage over its operational lifetime. Its onboard tape recorder, whose primary memory had already failed, partially failed on the Europa flyby that provided much of the critical magnetometer data. The Europa Clipper is designed to minimize cumulative radiation dose by spending most of its time in the less intense radiation environment, further from Jupiter, and making relatively brief, high-speed passes through the intense environment near Europa. Even with these precautions, the spacecraft is designed with radiation-hardened electronics and must contend with an accumulated radiation dose over its operational lifetime that is orders of magnitude higher than anything a spacecraft in Earth orbit would experience. The Europa Clipper carries 9 scientific instruments, each targeting a specific aspect of Europa's habitability. The most important for the fundamental habitability question are the following: the mass spectrometer suite, specifically the Surface Dust Analyzer, SUDA, and the Mass Spectrometer for Planetary Exploration, MASSPEX, will analyze the material directly. Europa's tenuous surface atmosphere and the plumes of material that may be erupting from its surface contain molecules from the subsurface. As the spacecraft flies through this material at high speed, the instruments will identify the chemical composition of individual particles and gas molecules. If Europa's ocean contains organic molecules, amino acids, fatty acids, nucleobases, other compounds relevant to biochemistry, and if those molecules are being carried to the surface and escaping into space, SUDA and MASPEX will detect them. the instruments are sensitive enough to detect individual molecules in specific mass ranges. The Ice-Penetrating Radar, REASON, radar for Europa, assessment and sounding, ocean to near surface, will peer through the ice shell using 2 radar frequencies to map its internal structure. The radar will distinguish between solid ice, liquid water pockets within the ice, and the ocean below, and will map the thickness of the ice shell across the hemisphere it scans. This directly addresses the question of how thick the ice is, a critical factor in how deep a future lander would need to reach to access ocean material, and whether the ice shell is dynamically active, with liquid water pockets that could facilitate exchange between the surface and the ocean below. The magnetometer, ECM, Europa Clipper Magnetometer, will measure Europa's magnetic field during each flyby with far higher precision than Galileo's magnetometer achieved. By measuring the way Jupiter's rotating magnetic field induces an electrical current in Europa's ocean and how that induced current modifies the local magnetic field, ECM will characterize the ocean's electrical conductivity. The electrical conductivity is a proxy for the ocean's salinity. Saltier ocean water is more electrically conductive and constrains models of the ocean's chemistry and the degree of rock-water interaction at the seafloor. The ultraviolet spectrograph, UVS, will search for plumes of material erupting from Europa's surface. Several potential plume detections were made in Hubble Space Telescope ultraviolet observations of Europa in 2012 and 2016, suggesting episodic venting of water vapor from the subsurface. These detections were controversial. The signal to noise was marginal. But if confirmed, plumes represent the most direct route to ocean chemistry, accessible to the spacecraft's instruments without the need to penetrate the ice. If a plume is active when the clipper flies through it, the mass spectrometers will directly sample whatever the ocean is venting. The thermal imager, Themis, Europa, thermal emission imaging system will map surface temperatures with high spatial resolution across Europa's surface. Regions of anomalously warm ice, warmer than their surroundings by even a fraction of a degree, may indicate locations where heat is escaping from below, which could correspond to locations of thin ice or near-surface liquid water pockets. These thermally anomalous regions are the highest priority targets for any future lander mission. The full suite of instruments working together across 49 flybys will build a comprehensive characterization of Europa's ice shell, ocean, and surface chemistry. The expectation is that by the end of the primary mission in approximately 2034, the scientific community will have a well-constrained picture of whether Europa's ocean has the chemistry and energy conditions needed for life. Chapter 5. Plumes. The smoking gun. We're still waiting to confirm. The discovery that could most directly transform the Europa habitability question from an inference to something approaching direct evidence is the detection and characterization of active water plumes erupting from Europa's surface. The concept of a water plume venting from an icy moon became scientifically concrete not from Europa, but from Saturn's moon Enceladus. The Cassini spacecraft, orbiting Saturn from 2004 to 2017, discovered in 2005 that Enceladus was actively venting water vapor, ice particles, and organic molecules from a system of fractures near its south pole. the famous tiger stripe features. The plume material was directly sampled by Cassini's mass spectrometer, revealing a chemical composition that included water, carbon dioxide, methane, hydrogen, and complex organic molecules, including compounds with molecular masses above 200 daltons, consistent with fragments of larger organic molecules. The discovery transformed Enceladus from an obscure icy moon into one of the top 2 candidates for extraterrestrial life in the solar system, alongside Europa. If Europa has similar plumes, the Europa Clipper could do for Europa what Cassini did for Enceladus: directly sample the ocean chemistry from a flyby without any need to land, drill through the ice, or access the ocean directly. The question is whether Europa's plumes are real. The evidence is as follows. In December 2012, the Hubble Space Telescope observed Europa in the ultraviolet during one of its transits across Jupiter's disk. In the data, there appeared to be a transient absorption feature, a brief increase in hydrogen and oxygen absorption near the southern hemisphere of Europa that was consistent with a plume of water vapor extending approximately 200 kilometers above the surface. The detection was at the edge of Hubble's sensitivity and was not confirmed in subsequent observations. In 2016, a second Hubble observation detected what appeared to be a plume in a different location on Europa's surface, again in the ultraviolet. Again, marginal signal to noise. But a follow-up analysis of the Galileo spacecraft's archived magnetometer and plasma wave data from a 1997 Europa flyby, published in 2018, found signatures consistent with the spacecraft having flown directly through a plume of plasma from a water vapor eruption during that pass, 20 years earlier, in data that had been sitting in the archive unanalyzed from the perspective of plume detection. The situation is, there are multiple independent hints of Europa plume activity, each individually at or near the detection threshold, but collectively suggestive. The Europa Clipper's ultraviolet spectrograph and mass spectrometer are designed to confirm or rule out active plume venting at a level of sensitivity that will either definitively detect plumes if they are there, at the level the Hubble observations suggest, or rule them out to a sensitivity roughly 10 times lower. Why is plume confirmation so consequential? Because if Europa is venting material from its subsurface, even just water vapor, then the ocean is in some form of communication with the surface. This communication could carry molecular evidence of ocean chemistry. It means the Clipper can potentially detect biosignatures, molecular signs of life, without any need to send a lander. If the plume material contains the kinds of complex organic molecules associated with biological processes, and if those molecules cannot be explained by abiotic chemistry, the scientific community would have something extraordinary, not proof of life, but a molecular anomaly requiring explanation. If plumes are not confirmed, if Europa's surface is genuinely sealed, with the ocean below the ice effectively isolated from the surface environment, then the path to any kind of life detection becomes dramatically more difficult. It requires a lander, and the lander requires drilling through kilometers of ice. And drilling through kilometers of ice is an engineering challenge of a different order of magnitude from any robotic mission yet attempted. Chapter 6: The Chemistry Question. What the salts are telling us. In 2023, Before the Europa Clipper even launched, the James Webb Space Telescope produced a result about Europa that changed one of the fundamental assumptions underlying the habitability models. JWST observed Europa in the infrared using its NIRS-PEC instrument to take spectra of the Moon's surface at wavelengths and sensitivities impossible from Earth-based observatories. The target was a region on Europa's surface called the chaos terrain, the disrupted, broken ice regions where models suggest ocean material has most recently been mixed into the surface ice from below. The specific finding was the detection of carbon dioxide on Europa's surface, and crucially, the detection of the carbon dioxide in the chaos terrain specifically, rather than uniformly distributed across the surface. This spatial distribution is the key result. Carbon dioxide is abundant in the outer solar system. It exists as ice on many surfaces. But CO2 on Europa's surface could, in principle, come from two sources: delivery by impacting carbonaceous meteorites, which would deposit CO2 uniformly across the surface, or production from carbon dissolved in Europa's ocean, carried to the surface through the ice shell in the chaos terrain regions. The spatial distribution rules out the meteorite delivery hypothesis. Meteorite impacts would deposit material more or less uniformly across the surface, not concentrated in the chaos terrain. The CO2 that JWST detected is concentrated exactly where the ice is most recently disrupted, where ocean material is most plausibly reaching the surface. This is the first direct chemical evidence that Europa's ocean contains dissolved carbon. Carbon is a prerequisite for organic chemistry. Every biomolecule we know of, amino acids, nucleic acids, lipids, carbohydrates, is built around carbon. The presence of dissolved carbon in Europa's ocean does not mean organic molecules are there. Dissolved inorganic carbon, carbonate and bicarbonate ions, for example, can exist in an ocean without any organic chemistry occurring. But the presence of carbon in the ocean is a necessary prerequisite for the carbon-based chemistry of life, and its detection by JWST strengthens the chemical case for Europa's habitability. The JWST result also provided new information about the specific spectral features of the surface ices. Earlier observations, particularly from ground-based telescopes and from the Galileo near-infrared mapping spectrometer, had detected a hydrated salt on Europa's surface, tentatively identified as sodium chloride, table salt, NaCl2H2O, or magnesium sulfate, which would be consistent with an ocean that had dissolved minerals from the rocky seafloor. The JWST spectra are more detailed than the previous observations, and the ongoing analysis is refining the identification of the surface salt species. The specific combination of salts in the ocean will provide constraints on the pH, temperature history, and rock composition of the seafloor, all relevant to the habitability assessment. The spectroscopic detection of hydrated salts on Europa's surface is one of the most powerful indirect arguments for a saline ocean in direct contact with rock. Pure water ice in space does not spontaneously generate sodium chloride. The salt must have been dissolved from somewhere, from a rocky seafloor being leached by circulating ocean water, and then delivered to the surface. The specific salt inventory on the surface is a chemical fingerprint of the ocean-rock interaction that has been occurring for billions of years in the subsurface. Chapter 7. Ganymede. the moon that has its own magnetosphere. If Europa is the most compelling habitable world, Ganymede is arguably the most scientifically fascinating because it breaks the expected pattern for an icy moon in ways that have profound implications for planetary science. Ganymede is enormous. With a radius of 2,634 kilometers, it is the largest moon in the solar system, larger than the planet Mercury, though less massive because of its lower average density. It orbits Jupiter at 1.07 million kilometers, completing one orbit every 7.2 days. Like Europa, it is in the Laplace resonance. It completes exactly one orbit for every 2 of Europa's and every 4 of Io's. And like Europa, its orbital dynamics drive some tidal heating in its interior. But Ganymede has something none of the other Galilean moons have: a magnetic field generated by an internal dynamo. This discovery by the Galileo spacecraft in 1996 was genuinely unexpected. Generating a magnetic field requires a conducting fluid in convective motion in the interior. On Earth, this is the liquid outer core of iron and nickel. For a moon of Ganymede's size and presumed composition, the expectation was that any internal heat would long since have dissipated, leaving the interior cold and solid. An active internal dynamo requires ongoing heat generation and a still liquid conducting layer. Ganymede's magnetic field is small, about 1% of Earth's field strength, but it is real. It is intrinsic to Ganymede, rather than simply an induced response to Jupiter's field. And it creates a magnetosphere, a region of space dominated by Ganymede's own magnetic field rather than Jupiter's. This magnetosphere is small enough to fit entirely within Jupiter's much larger magnetosphere, creating a nested system of magnetic domains that produces spectacular auroral emissions. Glowing rings of ionized gas at Ganymede's polar regions, produced by the interaction of trapped charged particles with the moon's own magnetic field. The Hubble Space Telescope observed Ganymede's aurora in detail in 2015, and the specific pattern of the aurora provided new evidence for Ganymede's subsurface ocean. The aurora's position should oscillate as Jupiter's large magnetic field rocks back and forth across Ganymede during its 10-hour rotation period. If Ganymede had no subsurface ocean, this rocking would cause the aurora to swing by about 6 degrees. But observations showed the aurora swinging by only about 2 degrees, significantly less than expected. The reduction is exactly what would be expected if a saltwater ocean inside Ganymede were generating its own induced magnetic field that partially cancels Jupiter's influence on the aurora. The ocean's conductivity was strong enough to damp the oscillation. The specific magnitude of the damping, 2 degrees instead of 6, constrains the ocean's depth and conductivity. Subsequent modeling has estimated that Ganymede's subsurface ocean may be up to 800 kilometers deep, far deeper than Europa's estimated ocean of 60 to 150 kilometers. However, the situation is more complex than Europa's because Ganymede's larger size and lower tidal heating rate mean that its ocean may be sandwiched between 2 layers of ice rather than in direct contact with rock. At the pressures found at the base of an 800-kilometer deep ocean inside a body of Ganymede's size, water ice takes on a different crystal structure, ice 6 or ice 7, that is denser than liquid water and would settle to the bottom. If the ocean floor is not rock but high-pressure ice, the potential for the geochemical reactions that drive hydrothermal chemistry and provide the chemical disequilibrium that might support life is significantly reduced. This ice sandwich configuration, rock below, high-pressure ice on top of the rock, ocean above that, regular ice above the ocean, and cold surface ice at the top, is a critical uncertainty for Ganymede's habitability. Europa probably does not have this problem because its ocean is shallower and the pressures at the base are lower, allowing direct rock-water contact. Ganymede's ocean, if it is sandwiched between ice layers, might be chemically isolated from the rock, an enormous volume of liquid water, but potentially one lacking the chemical energy sources needed for life. The Juno flyby of Ganymede in June 2021 was the closest spacecraft approach to Ganymede in 20 years, and the data returned has been transformative. The flyby provided new magnetic field measurements that are refining models of the internal dynamo, new plasma wave measurements showing the structure of the boundary between Ganymede's magnetosphere and Jupiter's, and new imaging of the surface showing previously unresolved geological features in the boundary regions between the ancient dark terrain and the younger grooved terrain. The grooved terrain, the lighter colored regions of Ganymede's surface crossed by parallel grooves and ridges, appears to have formed by extensional tectonics, similar in some ways to rift zones on Earth, suggesting that Ganymede's crust was at some point stretched and fractured from below by geological activity. Whether this geological activity is ongoing or ceased billions of years ago is one of the open questions the data is helping to constrain. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, is en route to the Jovian system, having launched in April 2023. It will arrive in July 2031 and spend its primary mission studying Ganymede specifically, making multiple flybys of Europa and Callisto before entering orbit around Ganymede in late 2034. JUICE will become the first spacecraft to orbit any moon other than Earth's moon. The Juno flyby of Ganymede on June 7, 2021, was the first close approach to Ganymede by a spacecraft since the Galileo mission's final Ganymede flyby in 2000. At closest approach, Juno passed within just 1,038 kilometers of the surface, close enough to return images at about 1 kilometer per pixel resolution over parts of the surface. The images revealed surface features at unprecedented resolution, including the sharpest views yet of the complex boundary between the ancient dark terrain, which has been heavily cratered and appears to be original crust from early in Ganymede's history, and the younger grooved terrain. The Juno plasma wave instrument provided a remarkable data point. As the spacecraft crossed from Jupiter's outer magnetosphere into Ganymede's mini-magnetosphere, it passed through the magnetopause, the boundary surface, and the plasma wave instrument detected a shift in the frequency of electromagnetic noise consistent with a sudden change in the ambient plasma density. The boundary was sharper and more clearly defined than the Galileo data had resolved, and the structure of the magnetopause gave new information about how Ganymede's magnetic field interacts with the Jovian plasma flowing past it. One specific finding was that the magnetopause had a more complex structure than the simple dipole field models predicted, suggesting that the interaction between Ganymede's intrinsic field and Jupiter's ambient field is creating magnetic reconnection events, the same process that drives auroras and substorms on Earth, at the boundary, affecting the distribution of charged particles in Ganymede's magnetosphere and potentially creating more complex radiation environments at the surface than had been modeled. The combination of Europa Clipper's Europa-focused mission and JUICE's Ganymede-focused mission represents an extraordinary investment in understanding the icy Galilean moons. And their complementary but different scientific emphases will provide a far more comprehensive picture of the Jovian system than either mission alone could achieve. Chapter 8, Callisto, the Forgotten Moon, with a surprising secret. Callisto is the unloved sibling of the Galilean moon family. It is the furthest out of the four, at 1.88 million kilometers from Jupiter, well outside the intense radiation belts that make the inner moons so challenging for spacecraft. It is the most heavily cratered body in the solar system, its surface and ancient, battered landscape essentially unchanged since the late heavy bombardment approximately 3.9 billion years ago. It has no evidence of recent geological activity. It has no mountains, no tectonic features, no volcanic terrain. It looks, bluntly, like a dead world. For decades, Callisto's role in the Galilean moon family narrative was to serve as the counterexample, the moon that did not differentiate, did not become geologically active, and did not develop a subsurface ocean. The standard interpretation was that Callisto's lack of orbital resonance with the inner three moons meant it received essentially no tidal heating. Without tidal heating, Callisto's interior cooled slowly and uniformly without the differentiation process that produced the layered structures of Io, Europa, and Ganymede. Callisto was supposed to be a primordial, undifferentiated mixture of rock and ice from top to bottom. The solar system's most accessible snapshot of the original building material from which the Galilean moons formed. The Galileo spacecraft made 17 close passes of Callisto during its mission, and the magnetometer data from those flybys complicated this simple picture considerably. The induction signal, the induced magnetic field response to Jupiter's rotating magnetic field, was present at Callisto too, just as it was at Europa and Ganymede. An induction signal requires an electrically conducting fluid somewhere in the interior. For Callisto to produce this signal, it must have a layer of conducting fluid, most plausibly a saltwater ocean, somewhere in its interior, despite having no tidal heating to provide the energy to keep it liquid. This is the Callisto paradox. The moon with no apparent energy source for a subsurface ocean appears to have one anyway. The resolution, to the extent it exists, invokes the presence of antifreeze compounds, specifically ammonia, in Callisto's interior water. Water mixed with ammonia has a freezing point significantly below that of pure water. An ammonia-water mixture of roughly 30% ammonia by mass has a eutectic freezing point of approximately minus 97 degrees Celsius. If Callisto's interior water contains dissolved ammonia in sufficient concentrations, the water remains liquid at temperatures far below what pure water requires. The energy needed to maintain a liquid layer is therefore lower, and the small amount of radiogenic heating from Callisto's rock component, which in the absence of tidal heating is Callisto's only internal heat source, might be sufficient. The problem with the ammonia hypothesis is that an ammonia-water ocean would have very different chemistry from the salt-water oceans of Europa and Ganymede. Ammonia is a reducing agent, and an ammonia-rich ocean would have different redox chemistry, different pH, and different capacity to support the kinds of metabolic reactions that drive the Earth's chemosynthetic ecosystems. Whether life could arise or persist in an ammonia-water ocean is genuinely unknown. The chemistry is possible in principle, but has never been tested in any relevant way. The Juno spacecraft made close observations of Callisto in its extended mission, and the data returned is still being analyzed. Preliminary results suggest that Callisto's surface, at the resolution Juno achieves on flybys, shows more diversity in composition than the ancient, uniformly cratered surface images suggested. There are spectral variations that may indicate compositional heterogeneity in the surface ice and rock mixture that wasn't well resolved in previous observations. Whether this heterogeneity reflects any ongoing subsurface processes or is simply the residue of 4 billion-year-old geological diversity is not yet clear. The JUICE mission will make multiple Callisto flybys, 21 in total, before focusing on Ganymede. The Callisto portion of JUICE's mission is specifically designed to refine the magnetometer measurements of the induction signal, providing better constraints on the properties of any subsurface ocean, and to characterize the surface chemistry at resolutions not previously available. If the ammonia-water ocean hypothesis is correct, the JUICE spectrometers may detect ammonia-related compounds in Callisto's exosphere, the thin gas layer near the surface, that would provide direct chemical evidence for what the interior ocean contains. The Callisto case has a specific implication for how we think about exomoon habitability that goes beyond the Jovian system. For decades, the search for habitable moons around giant exoplanets focused almost exclusively on moons in tidal resonance, moons that receive enough tidal heating to maintain liquid water without being too close to the central star. But if Callisto, which is in no significant tidal resonance and receives essentially no tidal heating, nonetheless has a subsurface liquid layer maintained by a combination of antifreeze chemistry and radiogenic heating alone, then the class of potentially habitable moons is not limited to those in tight resonant systems. Any icy moon large enough to have a significant rocky component, large enough for radioactive isotopes to provide meaningful internal heating, and whose ice contains enough dissolved volatiles, ammonia, salts, or other freezing point depressants to lower the melting point sufficiently, could potentially maintain a liquid layer. This criterion applies to moons that are much more distant from their parent planets than the Galilean system, and it applies to moons of planet types other than gas giants. An icy moon of a massive ice giant, or even a large Kuiper belt object with a captured companion, could in principle have a liquid interior if the anti-freeze condition is met. The number of candidate habitable bodies in the galaxy is potentially far larger than the tidally heated moon scenario implies. There are roughly 10 to the 11th power stars in the Milky Way, and many of those have giant planets. And many of those giant planets have multiple moons. If even 1% of the moons of giant planets in the galaxy are large enough and compositionally appropriate for antifreeze-mediated subsurface liquid water, the number of potentially habitable icy moons in the galaxy is astronomical. Whether any of those moons would have the chemical richness needed for life The right rock composition for serpentinization, the right organic inventory for prebiotic chemistry is unknown. But Callisto's paradox expands the space we need to consider. Callisto's potential ocean, if it exists, is probably not a high-priority astrobiology target. The chemistry, energy sources, and rock-water interaction that make Europa and Enceladus compelling are much less certain at Callisto. But Callisto's mere existence as a plausible ocean world, without tidal heating, forces a broadening of the criteria by which we identify habitable worlds. If antifreeze chemistry alone can maintain liquid water over geological timescales, then the category of potentially habitable icy bodies in the outer solar system is considerably larger than the tidally heated moons alone. Chapter 9: The Ocean Worlds Hypothesis. How many are there? The Galilean moons of Jupiter are the best-studied ocean world system in the solar system, but they are not the only one. Over the past 2 decades, a growing body of evidence has established that liquid water oceans beneath icy shelves are not a rare peculiarity of the Jupiter system, but a common feature of the outer solar system. Potentially the most common environment for liquid water anywhere beyond the Sun's habitable zone. The inventory of confirmed or strongly suspected ocean worlds, as of 2025, extends across the outer solar system in a way that would have seemed implausible to planetary scientists 30 years ago. At Saturn, Enceladus is the most dramatically confirmed. Cassini's direct plume sampling left no scientific doubt. Titan, Saturn's largest moon, has a dense nitrogen atmosphere, lakes and seas of liquid methane and ethane at its surface, and strong evidence for a subsurface water ocean beneath its ice shell at much greater depths. The surface liquid hydrocarbon chemistry on Titan is a separate potential habitability environment from its subsurface ocean, and one that is genuinely exotic because liquid methane at -179 degrees Celsius is a radically different solvent from water, raising the question of whether life could use it as a medium in the same way life on Earth uses water. NASA's Dragonfly mission, scheduled to land on Titan in 2034, will investigate this question directly. At Uranus, Miranda and Ariel show geological evidence for past internal activity. The outer solar system dwarf planets are a particularly rich source of ocean world candidates. Pluto's surprising internal activity and the possible subsurface oceans suggested by New Horizons, Data, Eris, and Makemake as candidates based on internal heating models, and Ceres, the largest asteroid in the main belt, with bright spots in Occator Crater, interpreted as the remnants of recent or ongoing briny water venting from the interior. The current estimate of the number of ocean worlds in the solar system, bodies with confirmed or plausibly existing subsurface liquid water, is between 5 and more than 20, depending on what level of evidence is required for inclusion. At the conservative end, the confirmed cases are Europa, Enceladus, and Titan, ocean portion. At the liberal end, including plausible candidates based on indirect evidence, the number reaches into the tens. This abundance is not coincidental. The physical processes that maintain subsurface oceans, tidal heating and radiogenic heating, are natural consequences of the dynamics of multi-moon systems around large planets and of the radioactive isotope content of rocky bodies. Any icy body large enough to retain significant radioactive inventory in its rocky component, and any icy body in a resonant orbit around a massive planet has a physical mechanism to maintain an interior temperature above the melting point of water. The outer solar system is full of bodies meeting one or both of these criteria. The implication for astrobiology is profound. If liquid water is the primary prerequisite for life, and if liquid water is abundant in the outer solar system in the form of subsurface oceans, then the outer solar system is not a cold, sterile wasteland. It is, potentially, the most water-rich part of the solar system by volume, and possibly the part with the most habitable liquid water, measured in cubic kilometers. The further implication, and this is the part that makes the field feel urgent, is that the principles governing ocean world habitability are generic. They apply not just in the solar system, but in any planetary system with giant planets and captured or formed icy moons. The Kepler and TESS exoplanet surveys have found that giant planets are common, multi-planet systems are common, and orbital resonances are common. The conditions for tidally heated ocean worlds around gas giant exoplanets are almost certainly widespread in the galaxy. If life can arise in the subsurface ocean of an icy moon, if Europa or Enceladus harbor life, then the galaxy is not thinly seeded with life around sun-like stars in narrow habitable zones, but richly supplied with life around the moons of giant planets everywhere in the galaxy that planetary systems have had time to form. Titan deserves particular attention in this ocean world's context because it presents two completely distinct habitability scenarios that are entirely independent of each other, a situation unique in the solar system. The first scenario is the deep subsurface water ocean, inferred from Cassini's measurements of Titan's obliquity and tidal deformation during its mission. Cassini found that Titan's rotation axis is tilted slightly more than expected for a fully frozen body, and that the moon deforms tidally by a slightly larger amount than a rigid body model predicts. Both observations are consistent with a liquid water layer at depth, decoupled from the ice shell above, that allows the shell to slip slightly relative to the interior. The deep ocean, estimated to lie roughly 50 to 100 kilometers below Titan's thick ice shell, is much harder to access observationally than Europa's ocean. It is buried beneath an ice shell orders of magnitude thicker, in a moon with a dense atmosphere that complicates remote sensing. But its existence, if confirmed, adds Titan to the subsurface ocean roster. The second and far more exotic scenario is the surface liquid system. Titan has lakes and seas of liquid methane and ethane at its surface, observed directly by Cassini's radar and imaging instruments, with specific sea basins including Krakenmare, Ligeamar, and Pungamari, covering a combined area larger than the North American Great Lakes. The surface temperature on Titan is approximately minus 179 degrees Celsius, well above the boiling point of methane at Titan's atmospheric pressure, allowing it to exist as a liquid. Titan has a methane cycle analogous to Earth's water cycle: evaporation from the seas, transport in the atmosphere, condensation, and rain. Titan's orange haze is produced by complex organic chemistry in the upper atmosphere, where sunlight and energetic particles break apart nitrogen and methane molecules and reassemble them into more complex hydrocarbons, which rain down onto the surface and accumulate over billions of years. Whether life could use liquid methane as a solvent, the way Earth life uses liquid water is genuinely unknown. liquid methane has radically different properties. It cannot dissolve ionic compounds the way water does, which rules out many of the chemical reactions central to Earth biology. But some theoretical chemists have proposed alternative biochemical frameworks that would work in liquid methane, using acetylene as an energy source and hydrogen as a reductant, producing methane as a metabolic waste product, with cell membranes made from acrylonitrile, which has been detected in Titan's atmosphere by ALMA. Whether this exotic biochemistry has actually arisen on Titan, and whether it would be detectable, is precisely what the Dragonfly mission will begin to address. The flip side is also true. If Europa and Enceladus, the most favorable ocean world environments we have direct access to, turn out to be sterile, that result will be scientifically important in a different way. It will imply that liquid water and chemical energy are not sufficient for life to arise, and will point toward whatever additional constraint, specific chemistry, specific geological context, specific origin conditions, we are currently missing. Either outcome from Europa Clipper changes our understanding of life in the universe. Chapter 10: The Radiation Problem. Could life actually survive near Jupiter? Every discussion of life in Europa's ocean eventually runs into an objection that sounds initially damning. Jupiter's radiation environment is among the most hostile in the solar system. The radiation belts surrounding Jupiter are vastly more intense than Earth's Van Allen belts. The particles trapped in these belts, electrons and protons accelerated to relativistic velocities, bombard Europa's surface continuously, delivering a radiation dose to the surface ice of approximately 10 sievert per day. For context, the lethal dose for a human being is 5 to 10 sievert total. Europa's surface receives a lethal human dose every day, every year, for billions of years. The surface of Europa is lethally irradiated. If life exists at the surface, in the surface ice, in the uppermost centimeters, it is being destroyed by radiation continuously. No known terrestrial organism could survive at Europa's surface. But the question for Europa's habitability is not about the surface. It is about the ocean, which is shielded from the surface radiation by kilometers of ice. How deep does the radiation penetrate? The answer depends on the particle energies and the shielding properties of water ice. High-energy charged particles lose energy as they penetrate material, and the depth at which they stop depends on their initial energy and the stopping power of the material. Electrons in Jupiter's radiation belts can be extremely energetic, up to tens of mega-electron volts, and the most energetic ones can penetrate a meter or two of ice before stopping. But the intensity of radiation falls exponentially with depth. The radiation dose at 1 centimeter below the surface is far lower than at the surface, and by a depth of about 1 to 3 meters, the dose is reduced to levels compatible with the survival of radiation-tolerant terrestrial organisms. The most radiation-tolerant organism known on Earth is Deinococcus radiodurans, sometimes called the world's most radiation-resistant organism. It can survive doses of up to 1,500 gray, a measure of energy deposition per unit mass, and recover with no apparent permanent damage thanks to an extraordinarily efficient DNA repair mechanism. The annual radiation dose at Europa's surface would eliminate Deinococcus radiodurans at the surface. But at a depth of a few meters in the ice, the dose falls to levels that Deinococcus could potentially potentially survive. At the depth of the ocean, 15 to 25 kilometers below the surface, the radiation from the surface is completely irrelevant. The ice provides total shielding. The cosmic radiation background at the ocean depth would be from natural radioactive decay in the rock and water, similar to what exists in Earth's deep ocean. The radiation environment at Europa's seafloor is not hostile. It is, in this respect, entirely compatible with life. The SU radiation issue for Europa's ocean is therefore not a barrier to life existing in the ocean. It is a challenge for life in the ice itself, and it is an operational challenge for any lander that needs to access ocean material at or near the surface. The surface radiation also has a beneficial effect. It is the radiation that drives the production of oxidants in the surface ice that, when delivered to the ocean, provide the chemical energy budget discussed earlier. Jupiter's radiation is simultaneously one of the threats to surface life and one of the energy inputs that could make the ocean more chemically productive. The demonstration that radiation-tolerant organisms can survive the radiation levels found below Europa's surface. Ice is not merely theoretical. It has been tested in the laboratory. Researchers at the NASA Jet Propulsion Laboratory and elsewhere have subjected Deinococcus radiodurans and other radiation-tolerant extremophiles to radiation doses simulating the environment at different depths in Europa's ice shell. The results have been published and are relevant to the question of whether Earth-like life could persist in the Europa environment. At depths of about 1 to 2 centimeters below Europa's surface, the radiation dose is already reduced to approximately 1 gray per year, within the survival range of Deinococcus. At 1 meter depth, the dose falls further, to levels that many ordinary bacteria could survive with active DNA repair. At 10 meters depth, the annual radiation dose is less than the natural background from cosmic rays that organisms on Earth's surface receive. The ice itself is an excellent radiation shield for anything inside it. One of the more startling experimental results in this context came from studies of organisms frozen in Antarctic ice cores. Bacteria have been revived from ice layers dated to hundreds of thousands of years old, in viable condition despite being frozen and without metabolic activity throughout. The organisms survived in a state of suspended animation, and while their DNA accumulated radiation damage during that time, they were able to repair it upon thawing. This is not directly analogous to Europa's environment. Antarctic ice is much less intensely irradiated, but it demonstrates the principle that microbial life can persist in ice over geological timescales, which is relevant to the question of whether any organisms that might have colonized the Europa ice shell from the ocean below could persist in a frozen state until the chaos terrain cycling returned them to the surface. There is also the question of whether the chemical energy available in the irradiated ice itself, the hydrogen peroxide and other oxidants produced by radiolysis, could support microbial life in the ice at the depth where radiation levels are survivable. If radiolysis produces oxidants in the ice, and those oxidants diffuse downward through the ice structure, while reductants produced by the underlying ocean diffuse upward, there would be a chemical gradient in the ice, a chemical energy source, at the depths where radiation is survivable. Some models of the Europa ice shell chemistry predict exactly this scenario. a habitable layer in the ice at approximately 1 to 10 meters depth, where both the radiation dose is survivable and a chemical energy gradient from radiolytic chemistry is available. This ice shell habitability zone is shallower and more accessible than the ocean, and if it exists, the Europa Clipper might detect biosignatures from it directly in the surface material during low-altitude flybys without any need to drill. The more nuanced radiation concern for any Europa lander is not the radiation in the ocean, but the radiation that the lander electronics will experience at Europa's surface while it operates. A lander sitting on Europa's surface for a few months would accumulate a radiation dose that would destroy unprotected electronic components, and even radiation-hardened electronics face a finite total dose limit. This engineering constraint, not the biological radiation hazard to any hypothetical life in the ocean, is the primary radiation concern for mission designers. Any Europa lander will need to be either heavily shielded, very short-lived, or both. There is one more radiation-related consideration that is actually beneficial for astrobiology. The radiation that bombards Europa's surface does not only destroy, it also synthesizes. UV photolysis and charged particle radiolysis of the simple ices on Europa's surface, water ice, sulfur dioxide, carbon dioxide, can produce complex organic molecules from simple precursors. Laboratory experiments simulating the radiation environment on Europa's surface have produced amino acids, nucleobases, and other biologically relevant molecules from simple mixtures of ices irradiated with high-energy particles. The surface of Europa is an active chemical factory, continuously synthesizing organic molecules and other compounds that could, if delivered to the ocean through the ice shell, supplement the chemical inventory of the ocean with pre-biologically interesting chemistry. The radiation that kills at the surface builds at depth. Chapter 11: What we'd actually need to find. The biosignature. Question: one of the most important and most underappreciated aspects of the Europa Clipper mission is how it approaches the question of what it would take to convincingly detect life. This is not as simple as find something that looks biological. The history of astrobiology is littered with claims that turned out to be explicable by non-biological chemistry, and the scientific community is appropriately cautious about premature announcements. The most famous example is the 1996 announcement from NASA that a Martian meteorite, ALH 84001, found in Antarctica, might contain evidence of ancient Martian life. The paper, published in Science by McKay and colleagues, identified several features of the meteorite that were taken as consistent with biological activity. Carbonate minerals associated with organic compounds, magnetite crystals with properties similar to those produced by magnetotactic bacteria on Earth, and microscopic structures that resembled extremely small, fossilized bacteria. The announcement was made at a press conference by President Clinton and received worldwide coverage. Subsequent detailed analysis over the following years found alternative abiotic explanations for each of the individual features. And the ALH 84001 life claim is no longer considered credible by most planetary scientists. The lesson: multiple lines of evidence, each individually consistent with biology, can collectively be explained by non-biological chemistry. The bar for a life detection claim is very high. For Europa, The biosignature hierarchy works as follows. At the lowest level of significance is chemistry that is consistent with biology, but not specifically indicative of it. The presence of organic molecules, for example. Organic molecules are widespread in the solar system, produced by abiotic chemistry in meteorites, interstellar clouds, and planetary surfaces. Detecting amino acids or lipids in Europa's plumes would be extraordinary and exciting, but amino acids and lipids are produced abiotically in meteorites and can be delivered by meteorite impacts to Europa's surface and potentially recycled into the ocean. A detection of organic molecules alone would not be evidence of life. At the next level is chemistry that would be surprising, but not impossible to explain without life. Isotopic fractionations, for example. Living organisms preferentially incorporate lighter isotopes of carbon, C12 over C13, in their biochemistry, because the enzymatic reactions that build biomolecules are slightly faster with lighter isotopes. A strong depletion of C13 relative to C12 in organic compounds in Europa's plumes would be suggestive of biological isotope fractionation. But abiotic processes can also fractionate isotopes. And without a very precise measurement and a very thorough inventory of possible abiotic sources, an isotopic anomaly alone would not be convincing. At the highest level of significance is chemistry that has no known abiotic explanation, a molecular or chemical signature that life produces routinely, but that non-biological chemistry does not. The strongest candidate for this category in the European context is a specific combination of characteristics: large, complex organic molecules with specific functional group chemistry and stereochemical characteristics that match biological production. On Earth, the lipids that make up cell membranes have specific chain lengths, degrees of unsaturation, and stereochemical configurations, predominantly the L-amino acid configuration rather than the D-amino acid mirror image, for example, that reflect their biological origin. Finding lipid-like molecules with the specific stereochemical and structural characteristics of biological lipids in Europa's plumes would be very difficult to explain without biology. The most powerful biosignature scenario for Europa Clipper is not a single molecule, but a coherent package. Complex organic molecules at concentrations above what abiotic chemistry can plausibly produce, with isotopic fractionations in the direction of biological processing, with structural and stereochemical characteristics consistent with biological origin, in an environment that the other instruments have established contains liquid water, chemical energy sources, and stable conditions over long timescales. The convergence of all of these lines of evidence would be compelling in a way that none individually would be. The Europa Clipper's mass spectrometers, SUDA and MassSpecs, are designed with this biosignature hierarchy in mind. MassSpecs, in particular, can measure the masses of organic molecules to a precision of about 1 part in 100,000, sufficient to distinguish different molecular formulas for compounds of the same nominal mass. This mass precision, combined with a library of expected abiotic organic chemistry from carbonaceous meteorites and laboratory simulation experiments, allows the instrument to look specifically for molecular patterns that are unexpected in the abiotic context. There is one more biosignature concept that has gained significant traction in the astrobiology community, and that the Europa Clipper is positioned to test: the concept of life detection by statistical deviation from expected chemistry. The idea is that life does not merely produce specific molecules, it produces specific molecular distributions. A mixture of amino acids produced abiotically in a meteorite follows a specific distribution. Approximately equal amounts of left-handed L and right-handed D stereoisomers, and a statistical distribution of chain lengths and functional groups that follows the thermodynamic expectations of equilibrium chemistry. A mixture of amino acids produced by biology is dramatically different. It is overwhelmingly composed of L amino acids, and the specific set of amino acids present reflects the specific set used in the proteins of the particular organisms producing them. If Europa's plumes contain amino acids or similar compounds, the stereochemical distribution, the relative amounts of L and D forms, is a biosignature detectable in principle by a mass spectrometer that can distinguish the two. The Europa clipper cannot directly measure stereochemistry, but the molecular mass patterns of specific amino acid derivatives can carry stereochemical information. There are also indirect ways to infer non-racemic amino acid distributions from mass spectrometry data, specifically by looking at the ratio of specific amino acid pairs whose abiotic production ratios are well constrained. If the detected distribution of amino acids deviates significantly from the expected abiotic distribution in a way that is consistent with selective use of specific stereoisomers, the pattern that biology produces, this would constitute suggestive evidence that requires further investigation. The challenge is that this analysis requires a very clean understanding of the abiotic baseline. What organic molecules does Europa's environment produce abiotically, and in what quantities? This question is being addressed in laboratory experiments that simulate Europa surface and ocean chemistry. Irradiating ice mixtures with the appropriate particle and UV fluxes, studying the products of hydrothermal reactions in water rock systems at the appropriate temperatures and pressures, and analyzing carbonaceous meteorites for the full inventory of organic molecules that cometary delivery might contribute to Europa's surface. The result of these laboratory studies is a growing library of expected abiotic organic chemistry that the Clipper data can be compared against. Any detection that falls systematically outside this expected library, any molecule or distribution of molecules that abiotic chemistry cannot plausibly produce at the detected concentration, is a candidate for further investigation as a potential biosignature. This is an area of active instrument development and mission planning for future missions. But even the Clipper's mass spectrometry data will provide constraints on the organic molecular inventory in Europa's plume material, establishing baseline chemistry against which any future, higher resolution measurements can be compared. Chapter 12. The Road to a Lander. Engineering the Impossible. The Europa Clipper mission, extraordinary as it is explicitly positioned as a reconnaissance mission, a precursor to something more ambitious. NASA's long-term roadmap for Europa exploration envisions a lander mission as the next step if the Clipper's results confirm the key habitability parameters and identify optimal landing sites. The development of a Europa lander, however, involves engineering challenges that are genuinely unprecedented in the history of robotic space exploration. The first and most fundamental challenge is the radiation environment. We have discussed the radiation dose on Europa's surface, approximately 10 sievert per day at the surface ice. For electronics, the relevant measure is not sievert, a biological dose unit, but Gray, and the specific damage depends on the particle spectrum and the electronics type. At Europa's surface, even radiation-hardened electronics would accumulate significant damage over a period of weeks to months. A lander that needs to operate on the surface for months to conduct the science campaign needed to characterize the landing site, drill or melt through a sample of ice, and analyze what it finds, must either be very heavily shielded or use a highly redundant electronics architecture that can tolerate individual component failures. NASA's preliminary design studies for a Europa lander concept explored shielding options using dense metals, lead or tungsten vaults, but the mass required for effective shielding is substantial and drives up the total mission mass significantly. The second challenge is access to subsurface material. Any life detection scenario requires accessing material that has not been sterilized by surface radiation, which means getting below approximately 1 to 3 meters of surface ice. The methods available for doing this are limited. Drilling through ice is well-established technology on Earth. The deep ice cores from Antarctica's WAES Divide project drill through 3,405 meters of ice. But terrestrial ice drills are large, heavy, power-hungry machines that operate in the benign environment of a research station with maintenance crews available. A drill on a Europa lander must operate autonomously in a radiation environment that damages electronics powered by a radioisotope thermoelectric generator or similar autonomous power source with no ability to replace broken parts. An alternative to mechanical drilling is the ice melting probe, a device that heats its nose to melt a downward channel through the ice, sinking under gravity as the ice melts around it. Ice melting probes have the advantage of using thermal energy rather than mechanical components that can break, and they can, in principle, reach much greater depths than mechanical drills. The Ice Mole, a German-developed ice melting probe, has been tested in Antarctic ice and in ice on the Morteratsch Glacier in Switzerland. However, the power requirements for melting ice are substantial, and maintaining enough power in the extreme cold of Europa's surface for an extended melting operation is a significant engineering challenge. A melting probe also cannot easily retrieve ice samples to the surface for analysis. It would need to analyze the melt water in situ, which constrains the analytical capabilities available. The third challenge is planetary protection. The Committee on Space Research has classified Europa as a Category 4 restricted body for all missions that contact the surface, the highest planetary protection classification outside of Earth return missions. This means that any spacecraft that lands on Europa must be cleaned to an extraordinary level of biological cleanliness to minimize the risk of contaminating Europa's subsurface with terrestrial microorganisms. The cleaning procedures required for Category 4 restricted classification include dry heat, microbial reduction of the entire spacecraft to an assembled bioburden below 300 spores total, a requirement that is technically achievable but adds significant cost and schedule time to the mission development. For a lander that must drill into the ice and access subsurface material, the planetary protection requirements extend to the drill itself, and any sampling system that comes into contact with the subsurface. Every component that could potentially reach the subsurface must be sterilized to a level that eliminates essentially all Earth life. The contradiction at the heart of the planetary protection requirement is uncomfortable but unavoidable. The mission is going to Europa to look for life. But in order to look for life, it must ensure that the instruments it brings cannot themselves carry life, because a positive result from a contaminated instrument would be scientifically worthless. The more sensitive the life detection capability, the more rigorous the contamination control must be, because a more sensitive instrument can detect smaller amounts of contamination. This is not merely a regulatory obstacle, it is a genuine scientific necessity, and it is one of the primary factors that makes a Europa lander far more technically challenging than, say, a Mars lander. The fourth challenge is the deep ice problem. Even if a lander can drill or melt to a depth of 3 to 5 meters below the surface, it is still 15 to 25 kilometers above the ocean. The material it will sample is surface ice that has been irradiated for thousands to millions of years, not fresh ocean water. If the ice shell is dynamically active, if surface material is being mixed into the deeper ice and ocean material is being brought to the surface, then even shallow surface ice samples may contain molecular fingerprints of ocean chemistry. But the time scale and depth of this exchange are uncertain, and a shallow sample may reflect primarily the chemistry of surface radiolysis and meteorite delivery, rather than the chemistry of the ocean below. The deepest possible life detection at the surface is therefore in regions of the youngest, most recently disrupted chaos terrain, where the time elapsed since the material was last in contact with the ocean is shortest, and therefore the ocean chemistry signature is least degraded by surface processing. The e-Themis thermal imager on the Europa Clipper is specifically designed to find these thermally young regions, the warm spots where the ice is thinnest and most recently active. These identified landing sites from the Clipper flyby data will be the targets for any future lander mission. Despite all these challenges, NASA conducted a serious Phase A design study for a Europa lander in 2016 to 2017, producing a concept that was technically feasible within the constraints of a flagship-class mission. Budget in the $4 to $6 billion range. That concept has since been superseded as the focus of the program shifted to Europa Clipper as the first step. But the engineering knowledge developed in the lander study has not been lost. It has informed the Clipper's instrument design and the identification of the specific measurements the Clipper needs to make to enable a future lander mission. The roadmap, as currently envisioned, runs. Europa Clipper characterizes the ice shell, identifies plumes if they exist, determines ocean chemistry from plume sampling if plumes are confirmed, identifies thermally active landing sites, and constrains the radiation environment at potential landing sites. This reconnaissance, completed by approximately 2034, produces the science data needed to design a lander mission, specifying the right landing site, the required drill depth, the analytical needs of the life detection instruments, and the radiation protection requirements for the specific site chosen. A lander mission, if approved and funded in the mid-2030s, could launch in the early 2040s and arrive at Jupiter in the mid-2040s. A sample analyzed from Europa's subsurface by instruments that have been specifically designed to detect the biosignatures of life in the context of Europa's specific chemistry could potentially produce a result, positive or negative, by approximately 2050. The 2016 to 2017 NASA lander study is worth describing in more detail because it represents the most concrete and rigorous engineering assessment of a Europa lander that has been publicly released, and its conclusions are both encouraging and humbling. The study team, led by scientists at JPL, designed a concept around a science payload of roughly 40 kilograms in a lander, with a total launch mass of several thousand kilograms. The key trades were between science capability, more instruments, more mass, more power, longer surface lifetime, and the engineering constraints of the radiation environment, planetary protection, and the cost cap. The primary science payload included a sample acquisition system capable of collecting ice and potential organic material from below the surface, a mass spectrometer for organic chemistry analysis, a microscope for morphological biosignature detection, a Raman spectrometer for mineral and organic identification, and a chemistry package for measuring redox state, pH, and ionic composition of any liquid water encountered. The most important conclusion of the study was that the mission was feasible. A Europa lander could be built within the technology base available to NASA at a cost comparable to a flagship mission, and could conduct meaningful biosignature science. The most important caveat was that the surface lifetime of the lander in the radiation environment would likely be measured in days to weeks, rather than months to years. The radiation damage to the electronics, even with significant shielding, would accumulate to the point of instrument failure within a relatively short operating period on the surface. This means the science campaign must be designed for speed. A lander that can sample, analyze, and transmit results within days of landing before the radiation kills the instruments. The concept that emerged from this constraint was a lander optimized for a rapid, intensive science campaign. Landing, deploying the sampling system immediately, conducting the core chemical analyses within the first few days, transmitting the results, and then accepting that the instrument degradation from radiation will eventually terminate the mission. A lander that works fast, rather than one that works for a long time. The analogy is less the Mars rovers, which have operated for years, and more the Apollo lunar missions, which landed, collected, and departed in hours to days. A generation from now. Within the careers of scientists currently starting their PhDs, within the lifetimes of most people watching this video. Conclusion. The answer that's coming. There is an argument that the search for life in Europa's ocean is the most important scientific program currently underway. Not the most expensive, not the most technically sophisticated, not the largest in terms of personnel or infrastructure, but the most important in terms of what a positive or negative result would mean for human understanding. If we find life, if the Europa Clipper detects a molecular biosignature that cannot be explained by abiotic chemistry, and if a subsequent lander confirms it with higher confidence measurements, the implications are staggering. It would mean that life arose independently at least twice in the solar system, in environments as different as Earth's sunlit surface and Europa's dark, pressurized submarine ocean. Two independent origins of life in one planetary system almost certainly implies that life is not a miracle, not a single cosmic accident, but a natural consequence of the physics and chemistry of liquid water in contact with rock and energy. If life arose twice in one planetary system, it has almost certainly arisen countless times in the billions of planetary systems in the galaxy. The universe would, in all likelihood, be full of life, and the Fermi paradox would become the dominant intellectual challenge of the century, demanding an explanation for why, if the galaxy is full of life, none of it has made itself known to us. If we find nothing, if the Europa Clipper and a subsequent lander both returned from the best candidate for extraterrestrial life in the solar system, with results showing only abiotic chemistry, the implications are different, but equally important. It would not prove that life is absent, because the ocean is vast and the sampling is limited. But it would place a meaningful constraint. Life is not easily detectable in the accessible surface chemistry of the best characterized subsurface ocean in the solar system. Combined with negative results from Mars and Enceladus, should they come, it would suggest that life's emergence from chemistry is a much rarer transition than the optimistic models predict. That liquid water and chemical energy are necessary, but not sufficient, and that whatever additional conditions are required are not commonly met even in favorable environments. Either result changes everything. The positive result is the most transformative discovery in human history. The negative result is a profound constraint on one of the most fundamental questions we can ask. Neither outcome is trivial. Neither leaves the world unchanged. And this is the context in which the discoveries from Juno's flybys of Io, the JWST carbon detection on Europa's surface, the confirmation of Ganymede's subsurface ocean, and the launch of the Europa Clipper should be understood. They are not isolated results or incremental steps in a program of academic interest. They are the successive chapters of a story that is converging on an answer. The first answer, if it comes in the expected time frame, that humanity will have to the question of whether we are alone. The Galilean moons have been studied for 415 years since Galileo first noticed them as moving points of light. In the next 25 years, we will send a spacecraft through the plumes of the most promising of them, looking for molecules that only life produces. That is an extraordinary statement about how far we have come. The Europa Clipper's first flyby of Europa is scheduled for 2031. Between that first flyby and the end of the primary mission in approximately 2034, 49 close passes will accumulate data on the ice shell structure, the ocean's magnetic signature, the surface chemistry, and the potential presence of plumes. The scientific community is already preparing the analytical frameworks for interpreting what the spacecraft finds: the expected abiotic chemical baseline, the distribution of surface salt compositions predicted by different ocean chemistry models, the ice shell thickness distribution predicted by different tidal heating scenarios. All of this preparation is so that when the data arrives, the interpretation can proceed as quickly and rigorously as possible. The Clipper mission has been in development for over a decade. Scientists who conceived the mission are now in the later stages of their careers. Graduate students who wrote their dissertations on Europa ocean models are now senior scientists running the instrument teams. The question of Europa's habitability has been the central open question in planetary science for a generation, and the mission currently coasting through the inner solar system on its 6-year journey to Jupiter carries with it not just instruments, but the accumulated curiosity of an entire field. When Galileo saw 4 points of light moving around Jupiter in January 1610, he could not have imagined that one of them harbored an ocean larger than all of Earth's. When Voyager photographed Europa's fractured, eerily smooth ice surface in 1979, the scientists staring at the images could not yet prove what they suspected. When Galileo's magnetometer found the induction signature of a saltwater ocean in 1997, the result was compelling enough to end the debate, but not enough to tell us what was in that ocean. The Clipper is going to tell us what's in that ocean. Not completely, not with certainty, but with enough detail to know whether the next mission is a lander. Every chapter in this story, the discovery from Voyager, the magnetic evidence from Galileo, the JWST carbon signature, the Juno volcanic revelations on Io, the launching of the Clipper, is part of the same investigation. The investigation is whether the universe has done, at Europa, what it did on Earth. Whether the physics of tidal resonance and liquid water and rock have led, in that cold, dark ocean beneath the ice of Jupiter's moon, to the same extraordinary outcome they led to in the warm, shallow pools of early Earth. The question is almost 4 billion years old. The answer is arriving. It will arrive in the lifetime of people alive today, in data from a spacecraft currently coasting through interplanetary space toward the largest planet in the solar system. What that answer turns out to be is the most important thing humanity has ever waited to find out.